impressed with the quotes on practice makes perfect, right? Remember, we all heard that our moms and dads say practice makes perfect. I was so enamored with all these quotes. I said, instead of one quote, I'll give you several quotes. Okay? Let me see what the other quote is. I like this a lot by Vince Lombardi. Vince Lombardi is considered one of the most famous American football coaches. When we say football, we say soccer, right? In India, American football is different. I assume you know what that is. So the main trophy is named after Vince Lombardi, a very famous coach. It's not just practice, it's perfect practice that makes perfect. Very true, right? Practice without goals is no practice at all. I like this too. He's a great motivational speaker, Zig Ziglar. You can Google him up. Fantastic speaker. I actually attended some of his speeches. Repetition is the mother of learning. Sorry, it's a little bit hazy because I couldn't get a crisp picture. I'll read it out to you. Repetition is the mother of learning, the father of action, which makes it the architect of accomplishment. So to accomplish anything in life, basically you need to practice. I don't know how many of you have heard this story called 10,000 hours. There's a study made by psychologists. Thank you, JNTV, for giving a nice quote. There is no path to happiness. Happiness is the path. You're absolutely right, and I'll share a story about that after I finish this one. Okay? So that is Zig Ziglar telling about 10,000 hours, right? There are some studies made by psychologists and sports psychologists and so on. The magic number is 10,000 hours. What they mean by that is, if you look at all the great athletes, right, sports people, whether it is a Sachin Tendulkar or Tiger Woods, right, or who is the famous tennis guy, Federer, Rafael Nadal, Djokovic, all these guys, to attain that level of success, if you study them, if you add up their total practice hours, it comes to 10,000 hours to attain excellence. That's where the 10,000 hours come into play. If you take a normal working day of 8-hour work day and 40 hours per week, right? It takes 5 years to become perfect. That's how much practice one requires, right? If you're going to apply the same thing in computer science too. Okay? If you practice all these things for 5 years, you'll become a super duper IT architect. And on a lighter note, with all due respect to the wonderful, highly educated, very intelligent girls in the class, just on a lighter note, I thought I'll put this quote too. I'm sure all the faculty members out there who are, again, no offense meant to anyone, please take it in a lighter vein, okay? I can tell you my wife knows everything, so I don't need to discuss anything with her. I just tell her, do whatever you want. It's amazing, actually, the quote that JNTV put, I said I'll share something with you. So that is I have a great, nice wall hanging in my house. Here on the wall, there's a nice wall hanging where this is the quote on the wall hanging. Okay? Except in the wall hanging, we don't say path, we say there is no way to happiness. Happiness is the way. Okay? So recently we invited someone for dinner. Okay, from one of those Indian billionaires. Billionaires, B with B, billion with a B. So then they like the code, they like that wall hanging so much. So before they left, I had to take it out from the wall and give it to them as a parting gift. So now I'm looking for a similar wall hanging. Okay. Okay. Now you know all those codes why I gave, right? Now the students would know. Faculty members, please facilitate for the next 10 to 15 minutes some exercises I'm going to show you. But today's focus will be after the exercise is getting into a discussion on binary search trees. A couple of classes ago, I introduced binary search trees, but that was a very preliminary introduction. So today, we'll do a much more formal, full-length class on binary search trees, where we'll talk about the concepts and the operations, and in particular, we'll also look at some high-level algorithm for insertion and deletion. Okay? Hopefully, I expect to finish that. And then I will basically some kind of a justification for what we call it as balanced binary trees. Okay, so at least at the end of today's class, if assuming we get time and we come to that point, I'll just lay the groundwork for balanced binary trees, which we will cover in the next class. So next class is Monday for you. So by Monday, we would have been done with Unit 5. Okay. Okay, we are all ready. Let's jump into the exercise here. Faculty members, turn on your videos there in your classes so that way I can see. Groups of 2 as always. Paper and pencil. Do the following things. Again, nothing very fancy. Just rehashing your concepts over and over again here. Okay. Time now is what, 11:10 for you or 12:10? We are what, 12:10 I think for you now, right? All right. Spring forward, fall back. Yeah, 12:10. 10:40, 11 for 12:10. So up to 12:20 or 12:25, you do this exercise. And then as you finish your question, type your answer wherever possible. Yeah, I think you should be able to type them in the chat. Okay? Type them in the chat and write it just to me, not to everyone yet, because I want people to work on it, right? I would like to see answers today from Aditya, Chaitanya, Pragati. I don't recall seeing answers from them off late, so why don't you make sure you type in your answers. $15 minutes starts now. Other 10 to 15 minutes. Start from the top and go to the bottom. Might take 15 minutes and some might take 10. That's why I gave a range of 10 to 15 minutes. Because by the time you come to the last couple of questions, you might need to spend some time. I'm going to type something here for everyone.
What are the conditions for a day to be called as complete? Full అంటే నేను 0 or 2 ఉండాలి. Complete అంటే నేను కాదు. రైతు ఈక్వేషన్ వస్తే ఇప్పుడు మనం కంప్లీట్ చేయాలి. ఇది కంప్లీట్ అయిపోయింది. ఓకే ఫస్ట్ నుంచి పెట్టాలి డెఫినేషన్ కానీ మైనస్ చెప్పండి. Symmetry, there is a unique part from the group node to every other node. They are false. Okay, a part from the node, 21 అనే నోడ్కి ఆ గ్రూప్లో ఎన్ని పార్ట్లు ఉన్నాయి ఎన్ని పార్ట్లు ఉన్నాయి మా 21 ఎన్ని only unique part, single part of the railroad train and the radio because we don't have cycle cloud. How do you define? Level number. Level and 80. Root level 0. Next రాయాలి అన్నారు. అప్పుడు ఇబ్బంది హైట్ లెవెల్ అంటే రూట్ దగ్గర నుంచి అన్నారు. హైట్ అంటే ఆ పాటలో నీకు పెట్టింది.
So Jntuk students, you can get a 5-minute break. I'll give 5 more minutes for the rest of the participants. So SVCW, how are you doing? Generally, you folks participate, DMS, all of you participate very actively. I need some answers from some of you. Okay. Who type in if you have done at least one, how many questions you have done. Each of you can type in something there. Not Jntuk, Kakinada, they have finished everything. What about DMS? Some have answered the question. That's excellent. That's good. DMS said they have answered. That's excellent. By the way, students, don't feel shy. But when I'm a student, even when I'm a faculty officer, sometimes even I don't know the answer, okay? I remember once I gave most of my tests are take-home tests, and I teach database courses too here, right? So I remember once I gave a take-home test on database on some kind of normalization or PLSQL procedure or something like that. And then poor student, they worked 5 hours to solve some problem, they could not solve it. And they came to me. Turns out even I could not solve it. I just created some problem on the fly. It was such a tough problem, I later decided maybe I did not state the requirements correctly. So those kinds of things can happen too. So there's no need to feel shy. The moral of the story is, hey, we know it or we don't know it, but at least we try. Okay, DMS is, what about Aditya? Anyone did anything? What about JNTUV, which is generally very active? Chaitanya? So these are the type of questions that would be given in a final exam, typically. Okay? So that's why I keep giving you a lot of these practice questions every class. Okay, we'll move on because I think I gave enough time, right? But it's okay, you will know answers based on some of the slides that I'm going to show you anyway, okay? So as we keep looking at different types of trees, some of the fundamental properties of trees, if you notice, I keep rehashing some of the fundamental properties with different pictures. So for those of you who did not answer, no problem. Here's another opportunity for you to learn, right? So I will speak less because you know this stuff. Then there's one of the questions I asked about unique path, right? There's always a unique path from the root node to every other node, okay? Now the tree that I'm showing here is not a binary tree, right? It's not even a tree, forget binary tree, because there are 2 paths to go to D from root, AD or ABD, right? So it's not a tree. You need to have a unique path in a tree. We know what successor nodes are, predecessor, so I won't discuss. Okay. The tricky part comes. JNT Kakinada, verify your answers again this. The tricky part comes when you talk about levels and height of tree, right? So how do you define a level? I like the way the definition of a level is given here, right? The number of edges in the path from the root to that node. So if I say level of C, then you can see from the root is A here, right? So root is beginning at A. So the number of edges to go from A to C is 1, right? Edge is that arrow which takes you there. So that means in this model, in this particular model, we are taking root at level 0. Okay? All right, pretty nice, easy picture to remember that, huh? So, very convenient way. Now, it does not mean that all authors and all papers would treat like that, right? We have seen examples in the past lectures where the root node is considered as level 1, right? So I've shown you plenty of examples where some authors showed root node as level 1. But I like this concept slightly better because it's easy to internalize in my brain, right? I tie to an edge. Okay, how many edges I traverse to reach that node? Okay. Now, if you see A, how many edges do I traverse to reach A? It's a root node. That's a beginning node. There are no edges. That's the starting point. That's why it's level 0. So I like this definition. Okay. Height of tree. Okay. Height of tree is nothing but the number of levels. Okay. So in this case, height of tree is 1 edge, 2 edge, 3 edge. Height of tree is 3. That's the maximum here, right? if this tree goes somewhere here, wherever the maximum level that you traverse, that becomes the height of the tree. Now, as it has clearly been written here, it says some books define h as number of levels minus 1. Okay. Now, why number of levels minus 1? Because they start at 1. If they do levels minus 1, they should start at level 1. Okay. So imagine if this level 0 becomes level 1, then everything increases to level 3 becomes level 4. But if you go back to the definition of the depth, number of edges to travel is 1, 2, 3. So that is 4, level 4 minus level 1. That is 3. So that is why in the case when the root is starting at level 1, the depth will be levels minus 1. Okay. Otherwise, typically, I recommend always starting at level 0. No edges travel, so it is at 0 level. Okay. Full tree. Somebody, as Madam was explaining to his students, full tree, and Jntuk Moocs gave it in a slightly different way. Every node has exactly 2 children, and all the leaves are on the same level. What did Jntuk Moocs say? They gave a definition slightly differently. Let me. Okay, Jntuk put some answers. That's good, Jntuk. You gave it. Let's see. What did Jntuk Moocs say? I'm just checking in the chat here. Every parent has 2 children. Every leaf has equal depth. So they call it as every leaf has equal depth. Okay, that's what this means, right? All the leaves are on the same level means every leaf has equal depth. So they put it in their own words, and in this case, it was put in a different level. Depth and level are the same, right? So as you can see here, all the children are in the same depth. Okay, not this particular picture, but I'm talking about the definition. Because this tree itself that I'm showing on the right is not a full tree. Because you see this at level 2, there is a node E, right? That is a leaf node, right? It's not at the same depth as the rest of the leaf nodes which are at level 3. Okay. Okay. Next question. What is the maximum number of nodes at some level L? Okay. Maximum. So nice graphic here. I like this too. This will come in handy as you prepare for your final exam. Okay. It's it is always less than or equal to 2 raised to L. Okay, if you can see the examples also here given very nicely. Okay. But the reference is, remember, in this case, this discussion, the reference is level 0. Okay. In the exam, if they ask you a question like that, you state your assumption. Right? When you do the final exam, your examiner may not be the same data structures facilitator, right? And we don't know who writes the exam for you, right? If they give you a question like this, then one of the first things that you have to do, if the problem statement doesn't say, you say, I'm assuming the level started at level 0. Based on that, the maximum number of nodes at some level L is equal to 2 raised to L. Okay. What is the total number of nodes N of a full tree with height H? Okay. It turns out it's basically a geometric progression, right? Going back to the previous slide, correlating that with this one, you will get a geometric series. I forgot all about my geometric series, arithmetic progression and all that, by the way. Okay. It basically comes down to 2 raised to H minus 1. Okay. You can verify that number of things. So that N equal to number of nodes. Now, if you work that equation out, turning the question to saying what is the height of a full tree with N nodes, you can see height is equal to log of N plus 1. which is nothing but order of log n in terms of time complexity. Okay. Now, why is the depth of a tree important? I mean, this is all setting the stage for you to say why we are learning all the good stuff, rest of the stuff, right? So H is important because all the tree operations, right? What are the tree operations we typically do? Insert, delete, or look for a key, right? Everything is determined in terms of the height of the tree. So more the height of the tree, it takes more time to figure things out as a rule, right? So you want to always have H in a way where the running time is less, okay? So that's why maintaining the height of the tree becomes very important. And we will talk about that when we get into the balanced binary trees, okay? The whole idea of balanced binary trees is to get a good handle on the depth of the tree or height of the tree. Okay. So what do we have here? Let's see. One second. Let me monitor the chat also. Give me a second. Okay. So we talked about maximum height of the tree with n nodes, right? If I give you n nodes, this is another nice question, exam question. What is the maximum height of a tree with n nodes and what is the minimum height of a tree with n nodes? So given n nodes and we want you to arrange it as a binary tree, right? Binary tree, we didn't say anything more than that, right? The different ways of arranging them, as you can see here, the figure A shows the 4-level tree. Figure B shows it's a 5-level tree. And figure C shows it's a 10-level tree. Each of them is a tree, right? Each of them is a binary tree, correct? Which one has the maximum height? The one in figure C. Right? Height is number of edges basically, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, some 11 nodes. So that's the height of the tree. Okay. But if you see the minimum number that we got is on the left, which is a 4-level tree. So if I have to find an element, now you go back to what we learned in the beginning sections of our course, right? Like remember an array? If I have to find an element in an array, I have to search through an element array potentially. So I have to do n times potentially, right? So it's called order of n. Whereas, if the level of a tree, if I'm searching for something, if this tree is organized, let's say this tree is organized in some sorted order. That's what the binary search trees are. Then we can show that I can get to what I'm looking at in log of n. Okay, log of n is certainly lower number than n, right? So that's why how to get to the right tree becomes the crux of a lot of computer science algorithms. Okay. So that is the answer. So maximum height is n, same as linked list. And minimum height of it be log of n plus 1. Okay, because 1 is kind of like we start with the root, right? So now the question becomes, how do we search a binary tree? Okay. So what does it say here? Start at the root. Okay, I'm starting at the root. And do you see something incorrect here? I know it's incorrect or duplicate values allowed. I don't know what the author meant here. So you search the tree level by level. This is one algorithm, right? You're saying, okay, I'm looking for some number, let us say 11. So I started the root. Do I have 11 there? No. Then I go to the next level. So I look 7 and 5. I don't have the value. Then I go to the next level, 2, 6, 9. I know why 2 is repeated, replace 2 with some other number like maybe 3. 3, 6, 9. It's not there. Then I go to the next level, 5, 11, 4. Okay? If I do that, is this better than searching a linked list? Definitely not. The reason is you still potentially have to search all the members of the tree. Correct? Is this tree ordered in any way? I don't see this as ordered in any way. If you do an in-order traversal of this one, do you get the numbers in sorted order? Yes or no? You will not get them because it's really an unsorted tree. So when you have something like this, just because it's a tree does not mean you automatically get the search to be log of n. Okay? If it's unsorted, there is no rule to it, then it could be just as bad as searching a list. Whether it's a linked list or array, I mean, pretty much similar, right? Slight differences, but the idea is the same. Potentially, you search all elements of that to find out if your element is there or not. Okay? So then how do we improve upon it? That is the justification, right? So how do we improve upon it? By using the concept called binary search trees. Okay? Not ordinary binary trees, binary search trees. So that means the tree has certain properties. Okay? So what is the fundamental property of such a tree, binary search tree? It's listed on the left. The value stored at a node is greater than the value stored at its left child and less than the value stored at its right child. Okay? That is the definition. Okay? So it is there in some kind of a sorted order. Can someone tell me why this is a better way? Now what happens when I am searching the tree? Why do we say that this is better? Which student can answer that? Why do we say binary search trees are the answer to solving the problem of looking for something in a tree? I'm giving him a minute to think. So why do we say that this solves the problem of the searching through an unordered tree? It solves the problem and somehow it has to improve our time to find the element, right? You all agree to that? Because the whole idea is you're saying we want to reduce the time it takes to find something, correct? So, in this case, what is happening is you start comparing as you traverse the tree, you start comparing what you're looking for with the value of the node that you are at. If it is less than the node value, then you go to the left. And if it is greater than the node value, you go to the right. If it is equal to the node value, you stop. So at every step of the way, you are eliminating half of the tree. Right? You either go to the left subtree or right subtree, or you stop when you find it. This is similar to what we have learned in an ordered list, right? When we are an ordered array, meaning some sorted order array, which we learned in the class, I start at the midpoint. I look up my key value with the midpoint value. If it is greater, then I go to the right side of the midpoint value. If it is less, I go to the left side. It's the same concept. So all of a sudden, your search time decreases. Okay. Interesting question here. Where is the smallest element in such a tree? And where is the largest element? Who can answer that question? So to answer that question, we need to know fundamentally the main concept of a binary search tree, right? I just told you that in a binary search tree, if you start at a root, anything lower than a root is on the left side, left subtree. Anything greater than the root is going to be on the right side. So we already know that fact. So based on that, you should be able to answer this question, right? Leftmost element is the smallest element. And of course, rightmost element is the largest element. Because of the way the tree is defined and how it is structured. By default, leftmost element gives you the smallest and the rightmost gives you the largest. Okay? We'll test it out. Okay, that's number one. Okay, hopefully I'm not going too fast, right? Am I going too fast or too slow or just like Goldilocks story, just right? If I'm going too fast, raise your hand. If I'm going at a comfortable pace, raise your hand now. I'm looking at DMS's video only right now. Am I going too fast or too slow or just right? If I'm doing it just right, raise your hand. Of course, if you're totally lost, also you can raise your hand. I don't think you're totally lost. It's a very easy concept. Okay, now, how do we search? See, everything follows logically by definition, right? That is the beauty of these binary search trees. Yes, you start at the root. I'm not showing you code yet, right? Code. Okay. At the end, I'll make you review the code. So you start at the root. Compare the value of the item you are searching for with the value stored at the root. Okay? If the values are equal, then you found the item. Otherwise, if it is a leaf node, it is not found, right? That means that's the only node that is there. Remember, a tree can be one node tree, correct? That's why you have this third condition. Continuing. So, if it is less than the value stored in the root, then search the left subtree. That means you are going to the left. If it is greater, then go to the right subtree. Okay. So you repeat these steps 2 to 6 for root of the subtree chosen. Right? So you're looking for value, you go to the left, let's assume. Then left, then C becomes the root here. Then you search for that. Apply the same steps, repeat, repeat, repeat. Okay? That is how you search a binary search tree because it's in some kind of a sorted order. The way it is in sorted order, by the way, you can do an in-order traversal and convince yourself that it is in a sorted order. That is the way to verify that a given tree is a binary search tree. Okay. The question is it better than searching a linked list? Based on the fact that I repeated it so many times, obviously the answer is better. Why? because you get a log n. At every step, you are eliminating half of the tree. Okay. So always searching a binary search tree is faster. Interestingly, where do you think binary search trees are used? One example, I actually thought about going in depth through that example, but I decided against it. But those of you who want to know where it is used practically, all the dictionaries that you have, anywhere you see hierarchy or dictionary, binary search tree concept is used there. Okay? What is the time? 11:19. Okay. Let me do one more slide and then let's take a short 5-minute break, stretch break, right? Now, how do you represent it? So we understood the concept. What is the concept? Instead of having an unordered tree, to make search possible, we use the binary search tree concept where all the nodes are ordered. Okay? You have some root. Anything less than the root goes to the left subtree, and anything greater than the root goes to the right subtree. And if you do an in-order traverse of the tree, you will see that the values go in a sorted order. Okay? Now, how do you represent that in a data structure? It's a data structure class, so we need to know that, right? So you have these things root. Okay, root always points to the root of the tree. And every node would have 3 fields, right? We kind of did this exercise this last class also. I mean, you do the struct for a tree node. So it has 3 things. One is the key value, then you have a pointer to the left subtree and a pointer to the right subtree. Okay? Potentially, you could have a pointer to the parent, which is nil. And as it says here, it's optional. Okay? And then this is a property that all the keys must satisfy. What we told in English is written in math here. This is the symbol V and the line is for all, right? For all y in left subtree of x, the key of y is less than key of x, less than or equal to. Okay? And then the second condition is for all y in the right subtree of x, the key of y is greater than or equal to key of x. Okay? So that is the property of a binary search tree. That's the example there. You can convince yourself that, okay? Great. Let's take a stretch break here. I'm losing my voice. I guess I need to get my hot cup of tea. Let's see, 5-minute break. Get up and stretch. Time. I'm going to place myself on. I don't want to stop sharing. I want to share. Okay. So you can see in this particular binary tree, you will get that conditions which are always met, right? I'll let you convince yourself without me going to each and every node, okay? So you can see here, when we talk about traversal of the tree, because of the property of the binary search tree, right, you will see that they can get printed in a monotonically increasing order recursively. That means if you're doing an in-order tree traversal, which is also called a walk, right? So you're doing a recursive if x not equal to nil, meaning not equal to null or nil. Then recursively said, then you do an in-order tree walk of left of whatever the value is. Print key of x. Then recursively you do the in-order tree walk right. That's what you do, right? We do the left, then print the key, and then go to the right. That's what in order is. So if you apply that algorithm, you'll get. Now, what does it mean? How long does the walk take, and can you prove its correctness, right? So this class is not meant to really talk about correctness and things like that. But okay, so to prove the correctnesses, you should prove that it prints all the elements in order and then it terminates. Okay. So the author uses the induction principle where size 0 means there's nothing there, right? If size greater than 1, then you first print left subtree in order by induction again. Okay, and you print the root, which comes after all the elements of subtree, and then you print right subtree. So using the concept of induction, we should be able to prove the correctness of that walk. Okay. Now it turns out when you query a binary search tree, remember I said in general it's order of the depth of the tree, right? Remember we talked about why H is important. H makes a big difference. Okay, depending on how the tree is constructed, you can expect to get log n. In the case for balanced binary tree, that's the second bullet. Okay, in general. And if you have an unbalanced tree where it represents a linear chain of n nodes, then you can get it as order of n. Okay, we saw that too, how you got a right skewed tree, right? So that's why whenever you're dealing with trees, it is important to maintain the balance of the tree. Not all the time, it's not possible all the time, but as close to a balanced tree as possible. Okay, to take advantage of the fact that time complexity would then become order of log n. So what are we doing here? Same thing, right? Similarly, tree search, right? If x equal to nil or k is equal to kx, we are done. We are returning the value of x. Otherwise, in line number 3, you see that the value k that you are looking for is less than key of x, and return tree search left. That means you go to the left, else you go to the right. Okay. Typical order is order of h, assuming the tree is almost balanced. Now here, the same algorithm, instead of showing a recursive algorithm, again we covered recursive as an iterative algorithm, right? You have written the algorithm as an iterative tree search. Same thing, while x not equal to nil, meaning the nodes in the tree, that's where the x, right? X is nothing but the variable which keeps changing and then and keeps getting the node of the tree. So while x not equal to nil and k not equal to key of x, meaning you are looking at the value, the k is what you are searching, search value, and x is the current node which you are comparing with the value of k. So that's what you do in step 2. If k is less than key of x, then you go to the left subtree, otherwise you go to the right subtree. So notice one thing here, we did not use a recursion, we use a while loop and then we iterate it through the entire tree. Okay, that's what we did here. Now why do we use iteration? Because it's more efficient on most computers. Okay, so we actually when we get into my advanced data structures class, we go more in depth into recursion versus iteration. Okay? Recursion algorithm is easy to understand as a rule. It's a very elegant code. But if you don't do it right, you could actually go into an infinite recursion too, by the way. Okay? Whereas iterative algorithm is a little bit difficult to understand, but it executes faster in most computers. Okay? So that's why most of the time they always say design recursively, meaning to understand it at the design stage, you design it recursively, whereas when you get to the implementation stage, you implement it iteratively. Okay? Now, that statement may not mean much to second year, first semester students. You just have to take my word for it, right? The intent is not to go deep in that. Okay. Now, remember at the beginning I said, hey, how do you find the minimum and the maximum? We already know that the minimum is the leftmost node and the maximum is the rightmost node, right? So you see some small piece of code there. Okay, while left of x not equal to nil, keep going to the left. Okay. Once you come out of the while loop, whatever x value you are left with, that is the minimum node. So equivalent code on the right gets you the maximum node. Okay. While right of x not equal to nil, do x equal x gets right of x. At the end of the while loop, you return x. Okay. So a little bit more detail, like basically we introduced, if you recall, we introduced the concept of predecessor and successor of a node, right? So successor of a node, as you may recall, is node x, is a node y such that the key of y is the smallest key greater than key of x. Smallest meaning it is the immediate one. There would not be anything between x and y in the lower layers of the tree. Because if you build your tree right, binary search tree, that would not happen, right? So that is a successor. And then, of course, predecessor is the opposite of that, right? Okay. And it gives you some, how you search for those things. I would not go into the details of this right now because it's all theory for you at this point. But it is there for you to review, and then I'll answer questions in the next class for this one. So I give you some pseudocode for successor, how it is done. Okay. You can see here, if right of x not equal to nil, okay, then return 3 minimum of right of x. Right? That's what we want, right? Always the minimum, because you cannot get something else which sits in between those two. That immediately suggests what is the next minimum. So that's why you use the word 3 min right of x. Okay. Okay. I will not go through the code as I said that one. Okay. Now the question remains, that was searching, but what about insert and delete? Right? Classic properties are you either try to find a value or you insert something or do you delete something. That's how we studied other data structures too, right? Give me a second, please. Hi, Kirti, you want anything, Amma? Okay. And my daughter just walked in. I needed a contact. Hey, you are making noise there. I'm in a class. Give me a second, guys. You got it? Can you take Phil with you? I'm still talking to my daughter. And she came here along with her dog came, so we are trying to ask the dog to go in. Okay. So how do we insert, right, into the binary search tree? Okay. Now while you're inserting, you have to make sure the binary search tree property holds have to change, right? Because the definition, remember, go back to the definition. Now by now you know that. Next class when you come, I would give an exercise saying, okay, what are the two properties of binary search tree? By now you can guess what questions I would ask, right? To review the material. Okay. So we have to ensure that one, right? So in your mind right now you should be thinking, oh my God, when I'm inserting, there is potential for changing the structure of the tree. Potential, right? You may have to rearrange some stuff. We don't know that. But at least in your mind you should start thinking along those lines. Okay. So here is an algorithm here. Okay. How do we insert? Okay. So you initialize y and then you get x. Okay. What does x point to? The root of the tree. Remember? So while x not equal to nil, meaning you did not reach the end, okay, then you are repeating the loop, that is the do loop, right? Y gets x, whatever the value is, okay, then you compare the keys. It should be key of y is less than, not key of z, right? This is key of y in line 5 is less than key of x. Then x gets left of x. Remember, if it is less, you go to the left. If it is less, you go to the left. And if it is greater than, you go to the right. That's what you're doing in line 6 and 7. Okay. Then you reset the value there. And you continue like that. Basically, by the way, I'm just glossing over the code because I do not know if this code is required for this class or not, but I put it in there. And then I'll give you some practice problems, right, to do that. Okay. So this is the algorithm for inserting into a binary search tree. But conceptually, what would happen is what we need to see, right? That is the intent here, right? So you have 56, 26, 200, and you want to insert some value there, okay? And if I have any value there or here or not. Let's look at this one only, right? So let's pick some value. Let's insert, let's say I want to insert 10. Okay? So if I want to insert 10, what would I do? First few steps. Let's try to understand the first few steps. So goal is to insert value 10. Everyone knows where 10 is going to go here, right? Where would 10 go? Can somebody tell me? What would be the parent of 10? Once I insert 10, what would be the parent of 10? Nobody is answering? 12. You got it. Yep. As simple as that. It's a no-brainer question, right? Okay. So let's see how the algorithm works, right? The goal is to insert 10. So x is pointing to root of 3. That means x is pointing to 56. You know this how I used to trace. I gave you some tracing samples. That's all I'm doing here. Okay. While x not equal to nil. X is not equal to nil because it's pointing to 56. Okay. Do y gets x. Okay. So that pointer. Okay. Now you're saying key of y is less than key of 6. Meaning wherever y is pointing to, okay, you compare the values. Then if the value is less, in this case, it is less, right? Key is 10 and 10 is less than 56. You go to left of x. So that means left of x would now have 26. Okay? You continue like that in that loop, and then at the end of that, you should be able to insert 10 underneath 12. Okay, that would be a task for you after we are done with the class. Go back and look at the code and trace it. Remember, I gave a lot of tracing exercises. So this falls under that category here. So if you were to analyze this algorithm, okay, we did a little bit of big O, theta and small o and omega, remember? So if you analyze this one, the initialization step takes only one, order of one. In one step you're done. If you look at the while loop, it's basically traversing the tree. Since you're traversing the tree, by default it's order of h. H is the height. Okay? Now once you come out of the while loop, right, then the rest of the steps begin, right? 8 through 13, where you are doing the actual insertion. Okay? And insertion is basically, even if you look at 5 steps, ultimately it's a order of 1. Okay? So if you eliminate all the smaller factors, that's the whole idea of complexity analysis that we learned in the beginning, right? If you eliminate the small order factors, the highest order factor remaining is h. So the total time in terms of inserting into a binary search tree is order of h. What is the insertion time analysis when we did for, let's say, to insert something into a linked list or an array? Those would be order of n. So you're getting a logarithmic advantage here when you have things stored in a binary search tree. Okay, that is the moral of the story. There's some exercise here. I left it in there. We are not doing it in the class, but later on, once I upload it, if people can try to do this exercise and post their answers in the community, that will be fantastic. Okay. The other one, when we talk about besides search and besides insert, is the case of delete. Okay. Now, what does tree delete mean? In the context of regular trees, we have seen delete, but let's look at it here carefully. Okay. So, you have different cases of delete. If X has no children, meaning there is only one root node, there is nothing else, right? One node tree. Then you remove that. Okay. Now you're deleting X. If X has one child, then what happens? The pointer of X should point to the child. That is case 1. Important. Interesting case, right? What if X has 2 children, meaning 2 subtrees? Then what becomes the root? If you remove X, one of the 2 children should become the root. Okay? So that's where you look at what the successor of X is. You swap X with its successor. Okay? After you swap, then you perform case 0 or case 1 to delete it. Okay? Again, it's theory. You would not understand, I'm 100% sure, by looking at this slide. But I think I do have again, the order of deleting of a node again falls under order of h, which is logarithmic. Okay? I did give some code there, pseudo code, right, to delete from a tree. Okay? Okay, which one we are deleting is given here, and then the code goes to 2 slides there. Again, you trace it after the class or the take-home assignment, and then you can post your questions in the community if you have any questions, or you can say, hey, this is how it works. You can post your answer. Okay? There's some slide, I didn't delete it, I kept it there. But just like how we did the correctness of insertion, we can also prove the correctness of tree delete. Okay? Ignore it for now. Okay? I'm not going to ask any questions on that. Okay? Now, where do we use binary search trees? Okay? As I mentioned to you earlier, we use them in dictionaries, in building dictionaries online. And then in the case of operating systems, we have this concept of priority queues that I discussed in one of the classes. We use this concept of binary search trees there as well. And then typically we use them because the basic operations take time proportional to height of the tree. That is order of H. Significant improvement over the linear structures like arrays and linked lists. Remember I told you I will show you code. This is the code there. If you recall, I showed you this code when I first introduced binary search trees. I said, hey, the code is there. I wanted you to trace. I don't know if you trace them there, but it is here. It's a pretty easy to understand code, right? There are two versions of the code. Okay. One is a recursive one on the top, and the other one is the iterative version. So what are we doing here? Searching. Pointer to the root, and then you're giving the search value, which is called a key. Okay. And the goal is return a pointer to the node that contains the key. And if there is no such node, return null. Okay. So you can see here, if it is not in the root, if not root, return null, meaning there is no root, meaning it's an empty tree, meaning there is no tree. That's what the first condition is. The second condition is key equal to root.data, meaning there is at least one node. Okay. If key is the same as root.data, then return a pointer to the root. Okay. Third one is if key is less than root.data, then you have to search root.leftChild, right? Because it has, every tree has the root, left child, and right child. So if keys is less than root.data or arrow data, you return the value of the search of the left subchild. That's why you see the search function is recursively called with the root left child and the key value. Now if that condition key is less than root.data is not correct, that means key is greater than root.data, then you go and do the return search of root of right child. Okay. See, just three statements. You take the baseline, and then you consider whether you have to go to the left subtree or you have to go to the right subtree. The same algorithm is written as iterative, right? Similar things. I'll let you convince yourself how that works. But similar concept, except it's not recursion. And again, it's of the order of H. I gave you some code into insertion into a binary search tree. Okay. Again, I want you to trace them after the class, right? I give you the code, I upload the document in the community. Then I want you to take one of the trees that we have seen in the class and use that as a data set, as a test data, and then go through these algorithms and see if the algorithm works or not on the data. Okay? Okay, so that is insertion code. Okay? Then you have this deletion. How do you delete, right? Delete is a little bit tricky operation. But anyway, I'll let you work on that, and then we'll review that in a little bit more detail based on the answers that you put in the community. We can discuss that in more detail in the next class. Okay. So that's what balanced binary search trees are. Predominant usage, search, insert, and delete can be performed in order of H time as opposed to linear time. Okay? Now, I also showed you an example today in the beginning of the class, saying that if sometimes the tree is not built right, it can stretch to many edges, right? That means the depth increases. So to address that problem, see this one here on the right side? It's an unbalanced tree because it has what is the depth of that? If you go from 50 to 78, you'll see the depth of that is 1, 2, 3, 4, 5, 6, 7. I'm counting the edges, right? Depth of it is 7. If you look at the left side, the depth of it is what? 1, 2, 3. 3 is the depth of the tree, right? So, how do we define it? A balanced search tree is one where all the branches from the root have almost the same height. They're not saying that they will always have the same height. It's almost the same height. That is the reason why the one on the left is called a balanced binary search tree and the one on the right is called an unbalanced binary search tree. So, as a tree becomes more unbalanced, search running time decreases from O log n to order of n. Because potentially you are going, it's like an array, right? It's of order of n algorithm. Because it turns out n, we want order of log n. Okay? That's where we say we want to keep the binary search tree balanced as we keep adding nodes or as we keep removing nodes. Because if you have a balanced search tree, insertion into a tree becomes reasonably fast. Okay? That is the main justification for a balanced binary search tree. I've been talking non-stop. Questions, comments? We are 2 minutes short of 12 anyway. So let me make actually 1:30. And did not give them any exercise, right? And I glossed over the code. The only reason I glossed over the code is I didn't know to what level of depth I needed to go into that code. If I look at the syllabus, it did not appear to me that I need to go in depth in that. It says give them the concept and no more than that. Okay? But since I did not go in depth, but I thought I'll still give you the code for you to trace, and then you come back, and then we'll discuss these things in a little bit more greater detail for the fun of it in the next class. Okay. I will pause here for a minute to answer any questions and comments. Faculty members.